So 2 lessons left in this unit, right? So there's, this is not on the test, okay? Applications of exponential functions, growth and decay, and the last lesson is on applications of logarithmic functions, and that'll take place Thursday after the test, which is Wednesday. So there are many applications of exponential functions, often known as growth and decay. Examples include population growth and decay, investment growth, radioactive decay, could do bacterial growth, stuff like that, right? So growth, be it natural or the exponential function y is equal to a c b to the b bracket x minus h plus k can be used for applications of growth and decay, but mostly we use a modified version. Y equals a times b to the t over p. A, b, and p are parameters. Y is the dependent variable, and t is the independent variable, usually time. Okay? And then actually what p is doing is it's modifying the time, right? Because order of operations says you're going to take t and divide it by p. So p usually takes t and converts it into some time unit that we want. This form is found on the formula sheet, therefore important. There are no translations of this, right? So for the function y equals a times b to the t over p, where t is greater than 0, it represents a growth function when what? B is greater than 1. It's a decay function when between 0 and 1. B is between 0 and 1. The y-intercept will always have a value equal to, so if you substitute t is 0, then y is equal to a, right? Because b to the power 0, 0 divided by p is 0, b to the 0 is 1, and so you get y equals a. So you have a y-intercept of a. Investigating the function y equals a times b to the t over p using graphs and tables of values. The graph shown represents the growth of an investment A over time t in years. Fill in the table below. Okay, so at 0 years, what's this worth? 1,000. 1 year? 2,000. I want in on this investment. 2 years? 4,000. 3 years? Let's not go quite that high, because it looks like 8,000. Either you can't double the number, or the a-intercept or y-intercept. So in this case, a for amount of investment. The a-intercept of the graph occurs where t is equal to 0, and therefore represents the what? Well, which part of the investment? The initial investment, right? That's what we're starting with. The principal. It's the principal amount, yeah. But we'll call it the initial investment. The initial investment. Yeah, it's good money, man. It's like, yeah. The initial investment is $1,000. Yeah. Got to bring more money into the calculus course, I think. Get your interest. Get your interest. Money, interest. Yeah, that was bad. Not intended, but it was bad. Since the y-intercept in the equation, y is equal to a times b to the t over p, is represented by the parameter a, right? We know that, so in this case, what do we know? A equals 1,000, right? All right, so if you're looking at a graph in that form, the y-intercept is the value of a. It's the initial, and it's also the initial value, or initial investment. This is a growth investment, so that we know for y equals a times b to the t over p that what? If it's growth, b is greater than 1. More specifically, since the value of the investment blanks every year, doubles, we know that you're going to double, then b equals 2. Yeah, so we know that b equals 2. Okay, so the y-intercept is telling us, hey, here's your value of a, and then the growth rate, if we can figure it out, it's doubling, then we get our value of b. Write an equation in the form y equals a times b to the t over p for this graph in particular. Use the form a of t, so the amount of the investment after t years. Use the table of values to help you figure out what p should be. So a of t, so we know we've got 1,000 times 2. Okay, so using the table, when time is 0, we've got 1,000 times 2 to the 0. Okay, that doesn't help us with getting the p. When we've got 1, it's 1,000 times 2 to the 1, which gives us 2,000. 1,000 times 2 squared, so what's the value of p? This down a bit. So we've got t. Do we need to modify the t? Or will this work if we just use straight t, right? So what's a of 3? Well, it's 1,000 times 2 cubed or 8,000. That's going to work, right? So the p value is 1. Okay. Use the graphing display calculator to verify the equation. Adjust the window to match the grid as shown. Okay, check. Okay, we've been there, done that. Wait, was there more on that page? Nope. If another investment doubles every 3 years, sketch the corresponding graph on the same grid and fill in the value to the right. Okay, so then we're still going to start with 1,000. If it takes 3 years to double, then that'll be 2,000. And then double again in another 3 years. And then I want that first investment. I want the one that doubles every year. I was halfway there. Fill the tables, graph it on the same grid. So let's go to the grid here. So we've got this guy here. It took 3 years to double the first time, and then another 3 years, and then another 3 years. Okay, so this is for 1e. Right, that's the graph for 1e. Sketch corresponding graph, check. Fill in the table, check. Describe a transformation that can be performed. So what transformation could you do on the first graph to get the second graph? Okay, so we're hearing stretch. What kind of a stretch? Horizontal stretch by a factor of 3. Okay, so if we look at, okay, let's go back. So horizontal stretch by 3, this will go nowhere, it's not being stretched. This is at 1, so it should go to 3. This is 2 units away, and now it's 6. 3 units away, and now it's not yet. So we've got a horizontal stretch by a factor of 3. And we go too far. Describe, so we said horizontal stretch by a factor of 3. Horizontal stretch by horizontal stretch by a factor of 3. About the y-axis.
After you write this whole thing in G.
Am I?
Yeah.
Okay, so we're still going to describe it. Horizontal factor of 3 about the so, but it's about the a-axis, right? But we'll call it the y-axis in brackets there. Yeah.
Can we go back to like the formula? Is the exponent, is that just for the 2 or is that for the whole thing?
This is for the graph we had initially had.
Yeah,
It's just for the 2.
That's just for this. Okay. Now we're going to develop the. So if A of t is equal to, represents the investment of $1,000, it doubles. If A of t is equal to, oh, so I guess we need a formula, right? In here. If A of t is equal to, represents the that doubles every, so the investment that doubled every year was 2 to the t. Then a horizontal stretch by a factor of, what was it, 3? About the y-axis produces the equation Okay, so what's going to give me a horizontal stretch by a factor of 3? What gets replaced with what? So t gets replaced by 1/3 t. We're going to write that as t over 3. Okay, which is now going to give us a p-value of 3, right? Which represents the investment of $1,000 doubles every 3 years. Okay, essentially what you're doing is taking time, dividing it by 3 to find out your doubling period, right? How many doubling periods? So 3 years, 3 divided by 3 is 1. 3 years it'll go through 1 doubling period. 6 divided by 3 is 2. 6 years it'll go through 2 doubling periods, right? 9 years it'll go through 3 doubling periods. Verify this formula with table of values in part E. Say we did. Okay. Well, you can verify, right? All right. Let's go back. And we're going to say we did it. We should do it. So I can find it for you. Oh, here we go. Okay. So 3 divided by 3 is 1. It'll be 2 to the 1. And 6 divided by 3 is 2. That'll give you 2 squared, and so on. Okay. So it has now legitimately been verified. Another investment of 1,000 is found to double every 15 years. It's more likely the one that I bought, but fill in the table of values. So at 15 years, it's going to be 1,000 times what? 2, because it doubles. In 30 years, it's 1,000 times what? 2 squared. In 45 years, it's 1,000 times what? 2 cubed. In 60 years, it's 1,000 times 2 to the 4th, right? Because really, what we're going to be doing here is we're converting years into doubling periods. Okay, so that's the idea. Use it to write the equation in the form. So A of t is, so our initial value 1,000, right? And that just comes from the graph. It's the y-intercept. The doubling, the b, because it's doubling. Okay, t is time in years. So what do we have to do with the time in years? So that when it's 60 years, we get. So t is going to be 0, 15, 30, 45, 60. What's p? Divide by 15, right? Because you want this to be equal to the 4, the 3, the 2, and the implied 1, the 0. Okay, so really the p is going, it's the conversion, right? It's actually the doubling period. P is the doubling period. Okay, and then t divided by p will be the number of doubling periods. Okay, and you'll take 2 to the power of the number of doubling periods, right? And we can work out what's it worth, in 25 years. What's it worth in 50 years? Okay, right, was that it for that page? Yes. Wait, I'm going the wrong way.
So if you had an investment that was like 10%, wouldn't you replace the 2 with like a 1.1?
So the investment, yeah.
Yeah.
Yeah, so it's the growth, right? It's how long it takes to grow.
I'll use this one.
The doubling thing or something for you. It's the rule of 72. There's a rule which you'd be able to figure out in a little while because of the math you know. It's called the rule of 72. If you take 72 divided by the interest rate you're getting, that's about how long it takes for your money to double. Okay, so if it's doubling every year, you're getting 36% interest a year, right? That's if you're getting, what do we get now? Like 2% if you're lucky, it'll double every 36 years. So you're not going to make money by leaving it in the bank to earn interest, right? It's just, there is no interest being paid effectively these days. So you need to invest it in the market. But then you can lose money too, right? So anyway. Writing exponential functions for applications in the form y equals a times b to the t over p. Y is the dependent variable and t is the independent variable, pretty much time. Y represents the amount after some time t. T will have the same units as p. So that's important. You got to make sure that these guys are in the same units. So if you're given like t in months, but p in years, you're going to have to convert one to the other unit, right? Like depending on the question. Y will have the same units as A. So again, that's all dollars or whatever. All right, so I guess we reveal stuff. Parameter A for Y is like you can just read it on your sheet. The parameter A represents the y-intercept, or in particular the blank amount, what were we using? Initial amount. Sometimes in financial circles called the principal. Parameter b. The parameter b represents the base of the exponential function, or in particular the multiplication factors. So if the population doubles, then b is equal to 2, and the increase is what? It's an increase of 100%, right? If the population triples, b is, and the increase is 200%, right? So remember, you're starting with an initial 100%. If you want it to double, you're going to add another 100%. If you want it to triple, you're going to add 200%. If the population halves, then b is equal to 1/2, or b is equal to 50%, and that's a decrease of 50%. Okay, sorry, that would be 0.5. And a decrease of 50%. Yeah, convert, so fraction to decimal to percent, right? To get a decimal to percent, just multiply by 100. If the population increases by 25%, then b is equal to 1 plus 0.25, or b equals 1.25. Okay, so the initial 1, the 1 in there, so even when we put a 2 in there as the base, we put a 2, the first part of the 2, the 1, think of 2 as 1 plus 1, and 1 is the initial amount, and the other 1 is what it's increasing, right? The population doubles, b is equal to 2. It's really 1 plus 1, okay, as decimals, which is 2, and if you want, then it's 100% plus 100%. If we're increasing by 25%, it's 1.25. The 1 keeps the initial amount, the 0.25 is the amount of increase, the 25%. If it decreases, it's going to be 1 minus, and so what would the b value be? 0.75. So that's the important thing, right? It's pretty easy. The increase is pretty simple because it's just 1 plus 0.25. When it decreases by 25, what we're really saying is this is how much is left. 75% is left. Okay? So when you're doing decay, when you look at that b value, you just think that's what's left. Okay? Like, you know, and if I want to know what am I taking off, I go 1 minus this and saying I'm taking off 0.25 or 25%, that's what's left. Parameter p. The parameter p is the time period it takes for b to occur. The p-value, as seen graphically, can be seen as a horizontal stretch factor. Example, if something used to double every year and now it doubles every 3 years, there had to be a horizontal stretch by a factor of 3. Some examples. For a population where t is in years, if the population doubles every year, what's p? 1. If it doubles every 3 years, p is... If it doubles every 3 months, okay, so if it doubles quarterly, then what's p going to be?
0.2. Or 0.
1 quarter, yeah, or 0.25. And basically what that means is you're going to quadruple your value, right? So for this last example, y equals a, b to the t over p would be written as y is equal to a, b to the what? So how would we write this guy? Well, t over 1 quarter or 4t. Oh, sorry. And if it's doubling, then we know that this is 2. Okay, so 4t. So if you're putting in 1 year, you're saying I'm going through 4 doubling periods, right? 2 years would be 8 doubling periods. You can get those interest rates, but you have to go to those special loan places. For a population where t is in months, if a population doubles every month, then p is equal to 1. If t is in months and it's doubling every month. If it doubles every 5 months, then p is equal to 5. If it doubles every year, that's 12 months and p is equal to 12, right? So again, what we're doing is converting a time in months into doubling. So if it doubles every year, we do 2 years, T over P. We do 24 months. We want to divide that by 12 to say, well, 2 years is going to be 2 doubling periods, right? So P is a conversion from time units into doubling periods, which is what the function wants. In summary, A, the initial amount, which is the blank of the graph, the y-intercept. B is equal to 1 plus growth rate as a decimal, or 1 minus the decay rate as a decimal. P is the time period it takes for B to occur, or the blank stretch factor, so the horizontal stretch factor. And Y is the amount after some time T. T and P, same units. All right, so you got to read questions carefully. Just watch out. It could be a time in years, but your doubling period might be in months. And Y and A must have the same units. They're basically just going to be dollars or number of bacteria or number of people if it's a population. Examples. Population P of a certain species is currently 500 and changes over time, T in years. Write a function that represents the population if it halves every year. Okay, so we'll go with P of T, population with respect to time. What's our initial amount? So 500. It's halving, it's halving. So what do we put in here? 1/2. Okay, and it's doing it every year, and T is in years. What goes up here? Just plain old T, right? Because T is in years, the doubling period. Okay, what change are you going to make if it halves every 3 years? Yeah, so we're just going to do T divided by 3, right? Doubling every 3 years will be a horizontal stretch by a factor of 3. And, or easily it's, well, I'll go through one halving period after 3 years. So I put a 3 in here, 3 divided by 3. I want it to be a 1. Right? When I put a 3 in there, I want a 1. I put a 6, I want a 2. I put a 9, I want a 3. Right? That's the number of halving periods. Increases by 20% every year. Okay, so initial amount. Okay, what goes in here?
1.2.
Yeah, 1 plus 20% is a decimal, 0.2. And it's every year, so what do we do with the P? Just T. Every 5 years, increases by 20% every 5 years. What change do we make? So T over 5, right? And just think about it. It takes 5 years to go up by 20%. 5 divided by 5 gives me 1. That would be a 20% increase. Decreases by 5% every 5 years. 500. What's a 20% decrease?
Minus.
0.8. So that's what's left, right? You're going to have 80% of the population left. And what's the T over 5, right? So it decreases, decay between 0 and 1. 1 minus 0.2. Always got to convert percents to decimals. 1 minus 0.2, which is 0.8 to T over 5. The value V of an investment after T months is given by V equals 200 bracket 1.04 to the T over 7. Complete the following statement. Initial investment of $200. Increases at a, so what's the rate of increase? 4%. So to figure out rate, if it's greater than 1, subtract 1, and then multiply by 100 to convert it from a decimal to a percent. Okay, so we have 1.04 minus 1 is 0.04, and 0.04 times 100. That's what goes in there. Every, 7 months, right? Because we're dividing by 7. The value V of an investment after T in years is given by V is equal to 3. Nice investment. That's my investment. I do that kind of. 3,000 times 0.83 to the T over 4. So my initial investment is, it decreases at a rate of 17. So here we go 1 minus 0.83, which is 0.17, right, times 100 to convert it to a percent. Okay, so you are left with 83% of your investment every. I've watched investments do that. And how long does it take to do that? Every 4 years. You'd think at some point you would sell, but you don't always. Okay. Growth, subtract 1, multiply by 100 to get the growth rate as a percent. Decay, subtract this from 1, multiply by 100 to get the rate of decrease. Okay, it's not decreasing at a rate of 83%. Although I have had some that do that. A certain biological substance doubles its mass every 5 days. Initially, there was 80 milligrams of the substance. 80. Fill in the table. So in 5 days, how much will we have? 160. And in 10 days? 320. And in 15 days? 640. Fill in the table of values, check. Write an equation in function notation that relates the amount of substance. So let's see, we're going to do A of t. So what's my initial amount? 80. What's it doing? It's doubling. So the base of the exponential function is 2. What's the doubling period? 5 days. So we go t divided by 5, and t is time in days. Okay. So remember, it's got to match up. Okay. Use the equation to determine the amount of the substance after 12 days. Round your answer to the nearest 10. Okay, so what are we going to do to get the after 12 days? Put in 12 for t, right? So we want A of 12. So A of 12 is equal to 80 times 2 to the 12 over 5. Okay? So show that work, and then after that, I think you can probably pretty much just punch it into the calculator. Okay? And we want to round to the nearest tenth. And what do we get? 422.2. Okay, remember the y value is in the same units as the a value, the little a, right? So it's 80 milligrams. This is 422.2 milligrams. Graphically determine how long, rounded to the nearest tenth, it will take for the amount to reach 1,000 milligrams. Now, we could solve this using logs, right? Because we know how. But we're not going to. Okay? And here's the deal. If it's a multiple choice question and you can do it graphically, like, why bother using logs if you know that, like I can just graph this? But you as a check.
No, they're not.
No. Why? Because I want to so you got to go y1 is equal to 80 1/2 to the t over 5, right? And y2 is equal to 1,000. And we're going to put in, so how long is it going to take? Well, so another 5 months will get us to 800. Another 5 months after that will get us to. So if we go to about 20, well, let's see, 640. So in 20 days, it'll be over 1,000, right? Was it one what?
Yeah, it's not one.
No,
It's
Oh, it's 2.
Yeah.
Yeah, at that rate. That'll be a tough one. It'll be like negative, right? It's like, yeah, a long time ago, 1,000. If we go up to 20 days, that should be enough because this will be 1280. Okay, so we can go show your windows. So x, let's go 0 to 20 by 1. Y, let's go 0 to, what do we want, 1,000? So maybe 1,200 by 200. You could draw a little sketch of your graph. It doesn't hurt to do that. I got to get a graph first. Oh, there it is. Open up. There we go. Clear. Okay, so y equals, so my y1 was 80, bracket 2, bracket 80. I got a nice dot on here. Okay, 80 2 to the power of, now I want a fraction. What's that? It's like this alpha, this guy here. Okay, so I want, now I can't use t, right? So x over 5. If you have an older calculator, just go to the power of, use the caret, and then go bracket x divided by 5 bracket. Okay, won't look as pretty as that, but 1,000 window. So we're going to go from 0 to 20 by 1s, and y min go from 0 to 1,200 by 200. Could have gone by hundreds, I guess, really. So 200s, we got what? 2, 4, 6, 8, 10. So it's here. That's around, what is that, like 2019? It's around 18 somewhere. Okay, now what do you do? Okay, so we can sketch this. Say 1,000. And then we want to find the x-coordinate of the point of intersection. And you need to state that. Okay, so at a graphical determine, show your y1 and y2, show your window, draw a little sketch, say what you're doing. We're finding the x-coordinate of the point of intersection. And what are we rounding to the nearest tenth? Yeah.
Why don't you just enter? There's only 2 of them.
Fine. 18.2. So it will take, what units were we in? Days. It will take 18.2 days. Use the graphing display calculator and the table of values in part A to determine the exponential regression equation for the mass of the bacteria culture. Round all values to the nearest hundredth. So in other words, now we want to run a regression. So we're going to take this. So follow along if you haven't run a regression lately. First step generally is I would go second function plus the memory and go to number 4, clear all lists. Okay, in this case, I don't actually have anything in there, but you know, if you're running a regression for the second time on the diploma or something, you're going to have data in your lists, so just clear it out. Okay, then go to stat, edit, and we've got what? 0, 5, 10, 15, and what was the other one? 80, 160. 320, 640, way to go, 64, 640. Okay. What kind of regression are we running? So go stat, over to calc. We want an exponential regression. It's actually below. Fastest way there is to go up because it's at 0, yeah. So you put in 0 or arrow to exponential regression. Your x list is the L1s, right? That's your x values. Your y list, that's your L2. Frequency, there is no thing here, no frequency. Store regression equation in y1, so go alpha F4 at y1. Okay, and then ask it to calculate. And it's 80 times 1.148698355 to the x. Now what that's doing is taking out this over 5, right? Round all values to the nearest hundredth. Okay, so we are going to write the table values in part A. Was it P of T? What were we writing? A of T? Okay. So A of T, or just write it out, Y. And what do they want? Nearest 10? Nearest 100th. 100th makes more sense. 1.15 to the x. Based on the regression equation, doubling every 5 days is the same as increasing by what percent every day? 15%. Okay, same as increasing by 15% every day. Every 1 day. The population of a town decreases at a rate of 2.3% each year. If the current population is 800, then algebraically determine the population after 5 years. Okay, so we need a regression equation, right? We need a decay equation for population. So P of T, what's our initial population? 800, right? So A is the initial population. What's our rate of decay? What's our B value? 0.97. Okay.
Yeah, 977.
All right. So it's 1 minus 0.023. Right. So you convert 2.3% to a decimal, multiply by 100. You go 1 minus that. So it's 0. What is it? 977. To current population is 800 every year, so just go to T, P of T, and T is in years. Okay. The decreases every year, so we don't have to modify this, right? T is one decrease period. Okay, algebraic determine after 5 years, so it's 800 times 0.977 to the 5, which is 713. Okay, so it is 712.1358. So if it's people, there's more than 712, because you can't have fractions of a person. So we take this and we round up and say there are 713 people. Okay? So if there's more than 712, we call it 713. Okay? So normal rounding rules don't apply. You can't say it's 712.1 people. No, there's no tenths of persons, right? So we're going to go to 713 people still left in town. Approximately. Algebraically determine the number of years rounded to the nearest tenth it will take for the population to first reach 500. Okay, so we have an equation. Let's rewrite the equation. P of T is 800, 0.977 to the T. Where does the 500 go? Right, when the population reached 500. Where does 500 go? T, P of T, big double choice here. P of T, it's a population, right? It's not an amount of time. So 500 is equal to 800. Step 1, do what? You're going to use log. What's the first step? Divide by 800, right? Okay. If you take the log of both sides right now, there's nothing wrong with it. You'll just end up with log 500 is log 800 plus t log 0.977, and then you're going to have to mess around. If you divide out the 800 to begin with, so we get 5/8. Okay. So before taking the log of both sides, if you can, isolate the power, right? Okay, now we take the log of both sides. Now I sometimes kind of shortcut this, right? Instead of writing equals log 0.977 to the t, I've taken the log, I move the t out front, right? So t is equal, or sorry, this, that's the unwritten thing, 0.977 to the t. Take the log of it. I just go straight to t log 0.977. So t is equal to the log of 5/8 divided by the log of 0.977, which I'm sure you could do much faster than me. So to the nearest tenth, what's t going to be? Yeah, I thought you could do it faster than me. 20.2. And the units are years, right? Let's go approximately equal, so we'll throw a little dot over that. So it's going to take approximately 20 years for the population to get down to 500 people at that rate. Anytime we do any of these things, we're always assuming that the rate of growth or decay remains constant, which is generally not a valid assumption, right? I mean, because other factors kick in.
Yeah, it's bad, yeah.
Mhm.
We could stop here and just like do this later and have some time to study.
Just go-
Just do the next question.
Well, we only have 7, 8, 9, 10. The rest of it's exercises, right?
Oh, okay.
So like, why not just finish it off? Okay, the other part's exercises, answers to which are in Schoology fully worked out. So, you know, let's just power through this.
Well,
It'll take another 15, 20 minutes, and then you'll have all day tomorrow, right? I mean, otherwise we got to pick the rest of this up at some point, right? Which will be tomorrow. All right, population of speed. We'll just speed up. We'll just crank it, shift into gear, higher gear. Population of a species is 500 on January 1st, 2000, and it increased to 700 by January 1st, 2011. Algebraically determine the annual growth rate to the nearest hundredth of a percent. Okay, growth rate. So P of T is equal to, our initial was 500, and it increased to 700, but how long did it take?
6 years.
6 years. So population, well, here, let's just write this out like this, and then we'll go 700. So the amount we have is 500 times our growth rate to the power of 6. We need to do this algebraically and divide both sides by 500, giving us 7 over 5 is equal to b to the 6th. How do we solve for the base? We go, nope. Yeah, I mean, you can do 6 log b, but you probably now you have a log of an unknown, right? So, 6th root, right? We take each side, so 7 over 5 to the 1/6 is equal to b to the 6th to the 1/6. So what's b equal to? I worked this out myself, you guys are not. How much? 12.06? Okay, I don't trust you. It's not that I don't trust you, but I don't trust you. Okay, my calculator's not working. What's b? I'll look on here. 1.0577. How did you get?
I heard her say 1 point something.
Yeah.
Oh, did she?
I didn't get
Oh, where did I get 12
I
point?
said 1.0.
Would it be 1.06?
Oh, okay, don't round yet. Because, okay, sorry, that's why I heard the 12.0. Don't round yet, because what's the growth rate looking at that? Yeah, see, so you've got to go, oh, well, now I have to subtract 1 from that to get 0.0577 and then multiply to get 5.8. So it's 5.8%. Okay, so like don't round this because this is not your answer. You have to subtract 1 from it multiplied by 100. So leave yourself a few decimals, okay, beyond, so that then you can do the rounding correctly. If you round intermediate values in a calculation, you're going to be off, and if it's a numeric response, it's just going to be wrong. Right? Like there's no, oh, but you know, I was close. Okay? So B is 1.0577, growth, subtract 1.0577, convert to a percent, 5.8%. And sorry, I wanted nearest hundredth of a percent, so I'm sorry, it's 5.77%. Okay? So that's why you have to carry enough decimals to get that out. Assuming the same growth rate, predict the population for January 1st, 2023. So how many years to 2023? 18, right? So we want P of 18, which is going to be the initial 500, 1.0577. Just use second function enter. You can pull that number back in, right? Or go up and pull it down to the power of 18. Okay? So pull this exact value out of your calculator. Don't re-enter 1.0577. Use the actual value. Just go 500 times, sitting in your calculator, just go 500 times second function enter, or go up and pull it down. And what do we get? $1,372. Came out exact, didn't it? Okay, so exactly 1,372 people. Okay, 3 more. 8. Radioactive substance decays from 2 kilograms to 400 grams. What's 2 kilograms? 2,000 grams, right? So we got to make sure that our units are the same. Or you could convert 400 grams to 0.4 kilograms. They just need to be in the same units. Algebraically determine the half-life of the substance, the time it takes for the substance to have half its mass, to have half its mass, to have half to the nearest hundredth. Sorry, it's half. So amount with respect to time, I'm going to say is little. Actually, we use a fancy letter in here. So A of t is equal to I naught, I sub 0. So the initial amount you'll often see written as I sub 0 for the initial amount. Okay, then we've got 1/2 to the t over p. That's a general formula. Okay, now it's got to decay from 2,000, so we're going to end up with 400 grams. We started with 2,000 grams. We know it took 15 days. So really, it's the value of p that we're trying to find, right? Because that'll be the half-life. So the question is, how many half-lives did you go through to get from 2,000 to 400? Well, you would have gone 1,500, 250. So you've gone through 2 and a bit half-lives. Okay? So it's 15 over something is going to be 2 and a bit. Well, let's work that out, right? So what do you got? So you got 400 over 2,000, which is 4 over 20, which is 1 over 5. So I have 1/5 is equal to 1/2 to the 15 over p. How do we solve that? Why is that there? Oh, that's the next question. That's why. What are you going to do? Take the what of what? Take the log of both sides. So the log of 1/5 is equal to 15 over p times the log of 1/2. Okay? If you like to, you can write another line in there. You could write log of 1/5 is equal to the log of 1/2 to the 15 over p. But it all comes down to this. All right, how do we solve for p? Multiply both sides by p. So p and divide by log 1/5. So it's 15 times the log of 1/2 divided by the log of 1/5. Oh, that's working again. Clear. So what did I say was 15 log 1/2 divided by log 1/5. Okay, so it should come out like, what, 5 point something, I think? All right, 6.46. So 6.46 days. the half-life. The intensity of the light below the surface of a particular lake is reduced by 4% for every 2 meters below the surface. Complete the table shown and write an equation in function notation that relates intensity to the depth in meters. Okay, so if the intensity of light is I naught, what percent of it is it at 2 meters? So it's reduced by 4%, so what's left? 0.96 I naught. I assume we're going to go to 4 meters then, it's every 2 meters, so then what's the next one? 0.96 squared. And at 6 meters? I know. Okay, so that should help us in writing the equation, right? To the depth in meters. So we want intensity. So what's the exponential, what's the base of the exponential? What are we reducing by? 0.96, right? So reducing by 4%, which means we have 96% of the original. Okay, and what are we going to do at D? What do we do to D? So if I put a D here for depth, how am I going to modify it so it fits this? Divide by 2. Yeah. So D over 2 gives us 1. D over 4, or D is 4. 4 over 2 gives us 2. 6 over 2. So we divide by 2, right? Which tells us how many times. So every 2 meters, right? So you take it. So if you're 10 meters down, you'll have gone through 5 levels of reduction of 4%. Determine the percent of original intensity remaining 10 meters below the surface. Round your answer to the nearest tenth. So I is equal to I naught 0.96 to the 10 over 2. Okay, so we can do that. So 0.96 to the 5th, right? 10 over 2 is 5. 0.8, what do they want? Nearest 10. So 0.8. It would be 0.8. I'd go more than a tenth on this though. That's percent. So sorry, percent. So we got to convert that to a percent. So 81.5%. 81.5%. All right, let's do this. 0.815. What comes next? 37 ... So 81.5%. Okay, so you'll be at 81.5%. At some, you're going to reach some, I don't know how much light you need to actually see, like we need to see. But at some point you're going to reach the point where you just can't see, right? And when you get far enough down, it's essentially pitch black. There just is no light that gets through.
6 photons in your eyes at 100 milliseconds. You can see dimly.
So you can see that? Okay. So it doesn't take much. You can see a candle on a mountaintop or something.
Very little.
Yeah, in low light. But down in the depths of the ocean, and there's creatures down there that have evolved with no, I mean, they don't need eyes because there's no light. So why, receiving light would do you no good. Infrared, that would, heat, that would do you good. Anyways, algebraically determine how far below the surface the intensity would be 30% of the surface intensity. Okay, so we need 30% of I naught. So our formula is I is equal to I naught 0.96 to the D over 2. I want 30% of the original intensity, which would be 0.3 I naught, right? 30% over 0.3. is equal to I naught 0.96 to the d over 2. So essentially, divide both sides by I naught. Doesn't really matter what the original intensity is. It just goes away now. So 0.3 is 0.96 to the d over 2. Solve. What are we going to do? Take the log. Log 0.3 is d over 2. Log 0.96. You want to get d, so multiply both sides by 2 and divide both sides by log 0.96, right? So 2 log 0.3. Show a little more detail. 2 log 0.3 is equal to d log 0.96. So d is 2 log 0.3 over the log of 0.96. And what do we want? Nearest tenth of a meter. Anyone? Anyone? 59.0 meters is what it's going to work out to. 59.0 meters. All right, last one. Compound interest. Now, Peter's saying, hey, pay attention to this, it's like money. Suppose an investment of $1,000 increases at a rate of 8% per year compounded quarterly. Good luck finding one of those, by the way, if you do. How do we deal with compounded quarterly? The equation needs to include the rate at which our money earns interest each time. What's the rate we need to multiply our investment by? So, a rate of 8% per year compounded quarterly means the investment actually earns how much every how often? So it ends 2% every 3 months, every quarter. Okay? So if you get 8% a year, but it's compounded quarterly, it means you get 2% every 3 months. It'd be nice to get 8% every 3 months, but you don't. So we cut the interest rate, we divide by the number of compounding periods, right? So 8% divided by 4. And it happens every 3 months. So our investment needs to be multiplied by, now what's the rate? 1.02, because it's 2%, every 3 months. To write the equation as it relates to the time t in years. Okay, so we have y is equal to, do we have some starting there? $1,000. Growing at a rate of 2%. And t, so t's in years, so what do we divide by? If you're getting it quarterly, you're getting it. So t is in years, you're going to divide by 4, because you're getting paid 4 times a year. Oh, sorry, no, you're dividing by a quarter. Because you're getting paid 4 times a year. Yeah, t divided by a quarter. So it's 1,000 for t. Okay, so it's quarterly dividing by, or just say, how many 3 months period are there in a year? There's 4 of them. So if this was like 5 years, that would be 3 quarters. So it's 4 times t. Speaking of 5 years, if the $1,000 is invested for 5 years, then algebraic determines the value investment at the end of the 5 years. Okay, so it's y is equal to 1,000, 1.02 to the 4 times 5, or 1,000 times 1.02 to the 20, which is, look on here, 1485.95. That's dollars, yeah, dollars. We ever do this? Okay, you want to see the power of compound interest? Let's say that 1,000 years ago, you had an ancestor who put $1 into a bank account, right, which paid 4% interest. So $1, 4% interest, 4% per year, slash A just means per annum or per year, for 1,000 years. And you now stand to inherit that amount. How much money is in that bank account? So how much does $1 if it gets 4% interest a year for 1,000 years? How much is it gonna be worth? $1.50, $25. Any guesses?
Let me calculate.
No, don't calculate it. Not yet. Just take a guess first.
Probably 100,000 or.
$100,000.
Actually, I'd say more.
More, a million, 10 million.
Because Benjamin Franklin did something like that.
So, a billion?
I don't know. I can't. I'm too scared to guess.
Take a guess.
Let's go to 100,000.
100,000? Okay. Anybody else?
It's much more than that.
It's much more than that.
A million.
It's exponential growth.
Million? Okay, so how would you work that out, right? So you got
Equivalent to the dollar.
$1, 1.04 to the end, to the 1,000 really, right? 1,000. Okay, so what do you, go ahead, work it out. 1.04 to the 1,000. What's the number?
1.079
Times 10 to the 17. So 9 is a billion. So we left a billion behind a long time ago. 12 would be a trillion. Power of 12.
Isn't this like one of the guys like?
15 to be a quadrillion.
When he put a wheat on every single chest and it doubled. And then
Yeah.
A lot.
It's like so the story goes that the guy who invented chess and the king said, "What do you want?" He said, "I put 1 grain of wheat on the second square, 1 grain of wheat on the first square, then 2 on the second, 4 on the third, just keep doubling it." And the king, who hadn't got that far in math, said, "Seems reasonable, right? But it's pretty large number." As is this, right? That's actually probably more money than actually is in the world right now. I mean, it's for like 10 and 17. That's 100,000 trillion. Big number, exponential growth.